Okay, so this problem here, last time we have finished explaining about this. I presented the full solution, right? So, but now here, I just want to draw your attention to some concepts here. So first of all, in part A of the question, okay, so homework problem like 1.10 here. In part A of the question, now I'm just telling you why I put the solution in this way. So first, the length of this path is called L, right? So L equals 1 kilometer, so that will be 1,000 meters. And then I stated that you consider the velocity of the student with respect to water, that's this one. So when it travels upstream, okay, so when it travels upstream, then the velocity of the student with respect to water is called V, right? And then you consider the So now let's look at here. V means the velocity of the student with respect to water. And this is the velocity of the water with respect to the ground. Let's say there could be some observer which stands on the ground, right? So on the shore and on the ground. So this is velocity of the water. I call it U, but actually some people call it V as well, right? With respect, water with respect to the ground is called U here. So when that person swims upstream, so that's what happens here. So now let's consider what kind of equation we should write down here, right? And what kind of velocity we are looking at. We are looking for the velocity of the student with respect to ground, because we actually need to obtain time, right? So last time, if you attended the previous lecture, there are 2 times the total time equals the time that for the student to travel upstream, and plus the time for the student to travel downstream. So this is upstream travel, the time, right? And this is the downstream travel. But the upstream travel, you consider delta T1 here, which should be equal to the path. So this is the path is with respect to the observer here, right? The observer which is fixed. So that observer is fixed at the shore, right? So that observer fixed. So that means that observer the velocity should be the velocity of the student with respect to ground. So now let's consider this idea here. So what we should consider is an equation like this. Velocity of the student with respect to ground should be equal to the velocity of the student with respect to water, then plus velocity of the water with respect to ground. Okay? So, and this quantity here we just say that this quantity here is the quantity we call V here. So the V we have told you here was actually this V. Okay? This V. The magnitude of this is the one I call V here. Okay? So this one I call this V as student with respect to water. That's the velocity that is given in the problem, and that is what I call V here. But the velocity of the water with respect to ground, that magnitude I call UW in my calculation here. So is that clear? Okay. So that's why that time should be equal to, you consider vector addition. So this is the vector for what? And this, we can consider that as the first vector, okay? First vector plus the second vector, but it's a vector sum. So when you can consider tip to tail method. That's the first vector, right? Second vector, when you do the vector sum, you should connect first you connect the tip of the first vector to the tail of the second vector, like in this way, right? And finally, when you want to get the resultant, this resultant should be equal to you connect from the tail of the first vector all the way to the tip of the second vector. So this will be your resultant here, right? So this one will be a resultant. So that's why the resultant should be this magnitude minus this magnitude. That's why the resultant, this red one is the one you put here. That will be V minus UW, right? So that's your delta T1. So if you saw my solution last time, right? I laid out a solution already. So that's delta T1 equals this. Now let's look at delta T2 here. Delta T2, you consider a different graph. Okay? So delta T2. Delta T2 is that person travels downstream. Okay? So downstream. Downstream is another case here. So downstream, let me draw it here. Right? That person travels downstream here. So that's V, right? But then the water flow will be here when that person travels downstream, like in this case. This is a different scenario, right? So this is UW. So UW is still flowing this way, but the person swims downstream in this way. So now look at the same equation here. We use this same equation here. Okay? This S stands for student, right? G stands for ground. So then you should do vector addition. Since now they point in the same direction, so when you do vector addition, to get this vector here, that will be this vector. You get the tip-to-tail method, right? Here. So that will be the red vector is the vector that you write down for when you compute time, right? So this is the velocity of a student with respect to ground, right? So this red vector here is the velocity of the student with respect to ground here, right? And here, similarly, this red vector is the velocity of a student with respect to ground here, right? Here I just point out the magnitude of it. So now delta T2 should be, let me write it down here. That's why delta T2 should be the length of the path and over the V plus UW, right? We have plus because now you do vector sum in this way. This is when the student travels downstream, okay? When she travels downstream, then you should do this vector sum in this way. And then that's why you do the computation in this way. So delta T1 plus delta T2, that will give you delta T. That's why delta T should be equal to L divided by V minus UW plus L divided by V plus UW. So that's the total time. Sorry, delta T. Okay? Delta T should be equal to delta T1 plus delta T2. That's the total time. And then you should obtain the answer in this way. Okay? So that's part A of the question. Okay? Part A of the question, that's this one. But part B of the question, when the water is still, it's simple. Right? Part B of the question, when water is still, then delta T prime will just be equal to, when water is still, you don't have this term. You don't have the second term here. So then that will just be equal to L divided by V plus L divided by V. Right? And part C of the question, you can just answer it. Okay? Answer it conceptually and write in words. Right? So you will see that this part A, this is part A. Part A of the question, you will see a longer time. Part B of the question, you will see a shorter time. So that means whether in part A of the question, you may save some time when you travel upstream. Right? So this is the upstream travel. It may look like you save some time. But then you will see that for the downstream, okay, sorry. So the downstream you save some time. I'm sorry. It may seem like for the downstream travel you save some time, right? The time is shorter for the downstream travel because the velocity is faster, right? But then for the upstream travel, you take more time actually, right? But here, that's the normal time that you have without the help of the current. Okay? Without current, you get this time here. But you will see that you save some time for the downstream travel, but it will take you more time for the upstream travel, but overall, it will take you more time than this case here, right? So that's your observation, right? So that's the answer to part C of the question. Is that okay for you? So you can compute, get the number, and you can compare, right? You will see that downstream, you will save some time. Okay? Compared to this trip, downstream will save some time, but compared to part B here, upstream will take more time. But overall, part B still take more time than part B, right? So that's the conclusion to this problem here. So I think this problem is related to daily life experience, but it's also not very easy to understand. That's why I explained about this here. So now let's move on to the practice question set. So here I'm talking about this practice question set for the exam here, right? So the first one we have already finished, right? First one, just different numbers, different numerical inputs. You can finish this problem quite easily. Okay, make sure that you truly understand what's going on here. Did you understand what's going on here? Yes, okay. So this context is relevant to daily life experience here. So make sure that you understand what we meant by this, right? So this context is actually called relative velocity. Right? So this velocity in section 4.6, but we didn't cover the whole section. We just picked the most important examples. We picked 2 examples. We studied that last time, right? One is this one, and the other is the other one in that first homework, right? So make sure that you finish first homework by tomorrow, right? So that's by Tuesday. So, right? So now let's move on here. Move on to the next one. Next one is a straightforward one here, right? So someone is undergoing a one-dimensional motion, right? So this one, you can solve it by kinematic equations, right? So this one, I think there's no need to explain. This is quite straightforward. Kinematic equations in 1 dimension, right? So now let's see if there are more challenging ones. The next one is also a kinematic equation, problem 3. Okay, so it's a kinematic equation. You have a constant acceleration, and you have the final velocity, right? And you have the initial velocity, and so on. So let me put that in this way. So the 4 kinematic equations will be, one will be this one, V final equals V initial plus A times T, right? So first equation, and so it's in the x dimension. So this should be called A sub x. The second equation will be x final equals x initial plus 1/2 V initial plus V final times time, right? And the third equation will be x final equals x initial plus V initial times time plus 1/2 times A times T squared. And the last equation will be V final square equals V initial square 2 times the acceleration times the displacement x final minus x initial. So those are the 4 kinematic equations in section 7 of chapter 2, right? These 4 equations. All right, so now let's move on from here. So again, by using those some of those 4 equations, you can also solve for problem 3 pretty straightforward, pretty easy. So now let's look at this equation here. It's a homework problem. You look at homework set 2. In the beginning, you will see such kind of problem here. How would you get the average velocity? Right? Average velocity. Let me erase this. Okay? Here we just test you about the definition, right? Definition of average velocity. But this question is also not difficult at all. Average velocity over a certain time interval. How do we obtain that? But pay attention. This is not average speed. Okay? We talked about average speed also before. So average velocity we should consider as follows. So this is problem 4. Okay? We can call that problem 4 of the practice set for the test. So average velocity, we can just call it V bar here. So should be considered as delta x over delta t, right? Displacement over time. It's different from average speed, right? So displacement should be considered as x final minus x initial, then divided by t final minus t initial. When you consider average velocity, only care about the final point and initial point. You don't need to care about the things in between, right? Just where is the final, where is the initial. Now, can anyone tell me, when you do the computation for this problem here, if you look at 2 seconds, right? 2 seconds, the velocity is here. And 8 seconds, the velocity is here. So should the average velocity be positive or negative in this case? Negative, right? Because 2 seconds, the x is higher, much higher, right? 8 seconds, x is 0, right? So then you should use final minus initial. So at this point it's 0. And at this point is, you take this value here, right? So you know how to compute this, right? 0 minus this value divided by a minus 2, right? A minus 2 is 6, right? So then you can finish the problem pretty easy, right? So that's problem 4 here. Now let's move on, right? Move on. So this is just about definition, and make sure that you also understand the homework problem here. This question, we spend much time talking about this. There will be such a question here, like multiple forces, right? And you can be asked to obtain either the magnitude or direction or both, the magnitude and direction of the net force. So are you able to do that completely, right? So you can also ask about direction as well, right? So for such kind of problem, you can also use the parallelogram method. I mean, conceptually, if you want to do it quickly to determine what's the direction of that force, you can also use the parallelogram method, right? By parallelogram method, I mean the following. So here, in this question here, I can also ask about direction. Here, I ask about the magnitude, right? I can also about what's the direction, what's the angle associated with the net force. But when you do such kind of problem, it's always good to consider conceptually where is the net force. So F1 is here, right? This is your F1, and here is your F2. And also have seen your F3 here, okay? F1, F2, and F3. F3, here you have 20 degrees here. So now let's first do it conceptually here. So you can pick any two of them and start to figure out the net force. For example, if you pick F1 and F2 first, and consider F1 and F2 as two adjacent sides of a parallelogram like this, right? So first, you virtually complete the parallelogram. Here, I didn't draw it to the correct scale. That's why the answer may not be very accurate, but here I just do it roughly. Okay? So the F prime, the sum of F1 and F2 is here, roughly here. But we are here, since I didn't draw it to the correct scale, it looks like it will point to the second quadrant. But still, we need to be careful when you draw the diagram, Here, I didn't draw it to the correct scale because this angle is not really correct, actually. So this angle is actually 60, right? So 60, we should draw it more carefully like this. But anyway, so this diagram will look like this, right? And then you start with F prime and consider F prime and F3. They will also form two adjacent sides of a parallelogram like this, right? Here. So then you can consider diagonal again, and this will be your F net. Yeah? You know your F net will be into the second quadrant. Then when you see the two components, then you do the algebra, right? Figure out the two components of F net. But if you do the computation correctly, you will see that your F net, there are two components, right? F net should be equal to something like Fx times I hat plus Fy times J hat. Okay? When you do a computation, you know that this Fx will be positive or negative. Negative, okay, will be negative. If my graph was correct, okay? If my graph is correct, then this is negative, then this Fy will be positive, right? Will be positive. So then you know the two components of F net. I can also ask about angle, right? If I want to ask about this angle, how would you obtain this angle here? Angle associated with F net. Angle, you should consider tangent theta, right? Tangent, suppose I call it angle in standard position, so tangent theta equals Fy over Fx, and then consider arctangent, right, of Fy over Fx. But this may or may not be just theta, right? You may get a negative angle, but you should interpret if it's a negative angle. Like when you consider arctangent, right, then you may get a negative angle could be like this one. This is the omega, right? Negative angle here. Then what you should consider, if you get a negative omega, so omega is this negative angle, then you should convert it to a positive angle. So that would be the phi here, right? So if you get a negative angle, convert it to a positive angle, phi here, and then you consider theta plus phi, right? Then you consider, so phi equals absolute value of omega, then you consider theta plus phi equals 180 degrees. Then you obtain theta. Okay? So that's how this works. Okay? So this kind of question is also important about chapter 3. Right? So now let's move on faster. This one we explained about this last time. Right? We explained about this last time. But also be careful. On the test, you may also see something like this. Here we ask you to compute the so-called average velocity, right? Average velocity for the entire trip. And here we consider a forward trip and backward trip, right? But now I can also ask you something like this. Consider several points here. So here, A, B, C. Okay? Let's consider 3 points here. Now suppose some person walks from A to B, okay, and with a certain speed. Okay? So and that speed, when that person walks from A to B, that speed is called V1. Okay? For example, and when that person walks from B to C, that speed is called V2 here. Okay? And then the distance between A and B is called L1. Distance between B and C is called L2. Then I can also ask you about what is the average speed from A to C. Okay? From A to C, a different problem. So this is like a variation. Okay, so this is like a variation of this problem here. From A to B, the person walks with the speed V1. From B to C, the person walks with the speed V2. And suppose the distance between A and B is called L1. Distance between B and C is called L2. Now, I'd like to ask about what's the average speed, V bar S, for the person from A to C. Okay? From A to C, find the average speed. Okay? Find this average speed here, V bar S here. So what is that V bar S? So be careful, what's the definition of average speed? It's the total distance traveled over the total time required, right? Average speed is the total distance d over the total time required. Let's call it delta t. So that delta t has two parts. So like such kind of problem, that delta t has two parts, right? D over delta t, but that delta t should have two parts. One is called delta t1. So that d now is, be careful, okay? Now d, the total distance now is L1 plus L2, right? So now delta t has two parts. One is called delta t1 plus delta t2. So that's how you should answer such a question. Again, here, this question is different from the one. This one I talked about this last time. There's no mystery here, right? But here I'm talking about a variation from that question here. Because you know that on a test, usually I change something, right? I'll not just copy the same thing to the test question. So now let's look at this thing here. How would you get this average speed here? So you should get the total distance L1 plus L2, right? But now you should consider the time for this trip from A to B, and then the second time. Delta T1 time interval from A to B, right? From A to B, that's time interval is called delta T1. From B to C, time interval is called delta T2, right? So then how would you solve such kind of problem here? So that then your VS, it means again, V1 and V2 will be given, like this problem here, the V will be given. But the 2L, this L, let's just assume that, because L1 and L2 will not be arbitrary. Let's say that L1 equals something like, let's say L1 equals 2L, right? For example, and L2 equals 3L, and L is some unknown parameter, right? L1 equals 2L, L2 equals 3L, and L is some unknown parameter, but we don't need to know L. So now let's do the computation here. How would you solve this problem? Your VS bar, V1 and V2 will be given like this problem here, right? But L1 and L2 will be given like this with the unknown parameter L. So L is unknown, okay? L is unknown. The lowercase l, small l is unknown, but the big L, we know the expressions, right? So now let's look at this thing. So that would be 2L plus 3L, right? Then how about the time? What's the time for time interval for this from A to B? Time will be equal to L over the speed, right? So that will be 2L over V1, right? And how about this time interval delta T2 here? That will be equal to 3L over V2, right? So that's how you get the average speed. But now you can extract a common L here, right? You'll see that L will be cancelled out, right? This L, although it's an unknown parameter, but once you carry out calculation, you'll see that this L, we can extract it, right? Extract it, and they will cancel out each other. You'll be gone, right? Then you can get the average speed if you know V1 and V2, right? So that's a variation from this problem here. So pay attention to such kind of question. Yes? Oh, it's just an assumption of my problem. I designed a problem so that these two, we know the ratio between them, but we do not know their actual length. So that's why I call it, I assume some unknown. We don't need to get that L. There's no need to know that lowercase small l. There's no need to know it. Do you see why? Because you extract an L here, extract another L here, and that two L's will got canceled out, right? This L and this L here will cancel each other, right? So we don't need to know that lowercase l. So here I just want to say that I don't actually know the distance. The L1 and L2 is not necessary to know, but I do need to know the ratio between them. Here is like I assume the ratio of L1 to L2 equals 2/3, right? I make this assumption because the ratio of L1 to L2, I assume that to be 2/3, right? And then I can make an unknown there, but eventually I don't need an unknown here. But this is some other question. Okay? This is not this problem. This problem was quite easy. You saw that in the homework, right? But this is something else. I want to draw your attention here. All right, so now let's move on here. Now let's consider problem 7 and 8. The baseball moving in the vertical direction. In that case, here on the question sheet, you will see those, right? But then so those equations, that's the free fall. Free fall, I listed the equation for you, okay? And those are similar to the homework problems. Make sure that you practice. But the difference between those many equations and the free fall, you have a new list of equations, right? For free fall, you have a new list of equations. For free fall, you need to pay attention that we should consider AY. Let me say again. Section 2.8, okay? Those equations will not be on the test. Those equations will not be printed, so you should write down on the note cards. Here I say that for free fall, you should consider AY equals negative G. Right? And what is G? G is negative 9.8, right? Meter per second squared. For free fall, you need to use the kinematic equations like this. Say V final equals V initial minus G times time, right? And so on. And second equation will be, so you can write those down by yourself, right? Y final equals Y initial plus 1/2 V initial plus V final times time. Right? Second equation. The third equation will be Y final equals Y initial plus V initial times time minus 1/2 G T squared, right? And then the last equation will be V final square equals V initial square, then minus 2G Y final minus Y initial. Okay? Those equations you should write down on the note cards, right? Because you need to know how to solve those problems. But if you know how to change from this to this, then it should be fine. If you know how to, I think most people you may need to write those down on note cards so that you don't forget, right? But we assume AY to be negative G, right? Negative. That's why you see negative G here. You can compare the difference between those equations, right? If you are not familiar with this, you should write down these things on the note card, right? Like this thing, right? So here you have negative 2G here. But otherwise, those kind of problems shouldn't be difficult. Those are actually from the homework. So if you go to the homework problems, you can see some hints there. If you wonder some hints here, right? This problem 9 is also straightforward, one-dimensional. Problem 9 is one-dimensional, so you should consider those equations there. And this question is quite simple, okay? But just pay attention to what we meant by angle and standard position. Yeah, this one was actually from a textbook example, actually. I point out on the guidance, so this is section 2.8. You'll see the example free fall. Okay, you see example here. You can try to study this, but basically this question, you also use those kinematic equations, okay? Free fall for the vertical motion here. Okay, so this problem here, so this we should explain a bit. So this question here, let's consider this one here. I'm sorry, need some space. Read this one first. This one may not be easy to understand. It's from the homework problem as well. I recommend you look at the homework problem. I believe there would also be hints there, right? But this, although it's a one-dimensional problem, so you should use those four kinematic equations. But be careful. When you solve this problem, this kind of problem is called a chasing problem. Okay? We can consider that as a chasing problem. So A chases B, for example, right? So this kind of chasing problem we do need to pay attention to as well. So again, the test will be on Wednesday, right? The first homework will be due on Tuesday, and the test exam will be on Wednesday morning. Make sure that you come a bit earlier to the test, right? All right, so. Okay, so now let's look at the next. This question, how do we solve it? There are two persons. Okay? One is called Brendan, and the other is his opponent. So then there are two. So these are two hockey players, right? And now let's consider the following. They want you to obtain the time that is required for Brendan to catch his opponent, right? So the setting looks like this: two hockey players, and so let's see, moving with a uniform speed. Okay, so the opponent moves with a uniform speed. So now let's consider the following. Consider two persons. Let's call Brendan person A. Okay? So this is problem 12. So let's call Brendan person A here. And the opponent, so first, there are two persons, okay? A and B, and Brendan, but I call it A here. Okay, so that's the major character, and B is the opponent here. So first, they met at some location first, okay? And now after they met at some location, this person B continue travels with a uniform speed. Uniform means constant, okay? Uniform. When you see the keyword uniform, that means constant speed here. And now person B will continue travel, okay? Continue travel with a constant speed here. And after a certain time, say 2 seconds. Okay, so that 2 seconds is some spatial time interval. We can call that, say, T star or something. So that person B travels with a uniform speed. Let's call it VB, right? So that means that they met first at a particular common location. The vertical part means location. So this we can define as x equals 0, for example. Okay, they met at a common location. Then afterwards, Brendan didn't move, but then that opponent keep traveling with a constant speed. Let's call that constant speed. Is that known? Yes, constant speed is known, right? So that VB equals 2 meters per second, which is known for this problem here. And then the person travels for 2 seconds. Let's call it T star, okay? T star means that 2 seconds. So that 2 seconds here, okay? So that person continue travel for 2 seconds, and then Brendan will start to move. Okay? Brendan will start to move after this time. So then that person will continue the motion with some unknown time. So they said that how much time does it take for Brendan to catch his opponent? So what we need to be careful is as follows. Suppose after this time, then let's say Brendan and his opponent have the same watch. Okay? So their watch are synchronized. So let's call this T equals 0 at this. So the T equals 0 for Brendan was located here, right? So this is the spatial location for Brendan, spatial. Okay, so here I talk about when spatial location for Brendan at T equals 0 is here, right? But the spatial location for his opponent was actually here, right, at a different location, but this was the same t equals 0. Okay? Their two watches are synchronized. So now let's consider the following. Now they will start traveling here. So here you will see that that person will travel with VB times time. And this is the time starting from here and all the way to the end. And here, also, t equals 0 is here, right? Suppose they both travel toward the end. The final time, let's just call it t. Okay? Final time, let's just call it t. And then at the final time, Brandon catches his opponent here at the final time here. So how long did Brandon travel? The distance that Brandon traveled is 1/2 times the acceleration of Brandon. I call it AA. Okay? AA means the acceleration of Brandon times the time squared. But now, you can see that the distance traveled by Brandon is called, the distance traveled by Brandon, let's call that XA. Okay? So the distance traveled by Brandon overall displacement is called XA. Displacement for the other person is called XB. We should say that XA equals XB. Right? And what is XA? It's 1/2 times A times T squared. That's the distance traveled by Brandon for the whole entire trip. What's the distance traveled by his opponent? That will be this plus this, right? So that will be VB times T. So see, T is a variable, but plus VB, the same VB times T star. T star is a constant, it's known, right? See, T is different from T star, do not get confused. There is a quadratic equation in time, right? So you have 1/2 AA T squared minus VB times T, VB times T star equals 0. Pay attention, this is a constant, right? Then you solve for T. Is that clear? Solve for time, but time should always be positive. So you should keep the positive solution, but drop the negative solution, right? So it's a quadratic equation in time. Did you see that? This is quadratic equation in time, but T star is a constant. T star is known. T star is here, right? It's a constant. So then solve for time. So what is time? There are two solutions. Drop the negative one, keep the positive one, right? But also go back to the homework. They will also ask you, homework, there's a part B of the question. They will also ask you, how far does Brandon travel during this motion, right? So once you know time, you can substitute that into here, you know how far. But this question, they only ask you about the time, right? What is the time that required for Brandon to move for the entire trip? So that's it. Okay? So thank you, and hope you have a great day.